let's talk a little bit more detail about how we look for biosignatures of gases produced by biology in the atmospheres of extrasolar planets. Well, we've already seen that the most likely signs of life are certain atmospheric gases, for example, oxygen produced by photosynthesis and ozone, the product of the reaction of oxygen with starlight. Methane and sulfur compounds might be other approaches to search for life or the signatures of life in extrasolar planetary atmospheres. How would we detect these gases? Well, it turns out that when light is absorbed by a gas and then subsequently transmitted, it produces a spectra with absorptions that correspond to the particular gases in that atmosphere. And these absorption troughs, if you like, you can see an example of some dips in the light that are caused by particular elements in the spectrum from a star. We can use a similar process to look for dips in the spectrum of light caused by particular gases. And these dips in the light give us telltale signatures of particular gases in a planetary atmosphere. Now you'll understand that it's very difficult to detect these spectra from extrasolar planets. Exoplanets are very far away and they're often very close to bright stars, so trying to pull the spectrum out of a particular planet alongside that huge amount of light being given off by a star is a very difficult thing to do. What you want to do is capture only the radiation being given off by the planet, so you can look for that biosignature. A couple of ways you could do this, for instance, is to take the spectrum of light given off by a star and a planet, and when the planet has rotated around the backside of the star, you could then get a spectrum of just the star, and you could subtract those two spectra to find the spectrum of just the planet. Other ways are to try and block out the light from the star so that you're only picking up the light from the planet in a telescope, and then look at the spectrum to see whether you can find a biosignature of gas. Increasingly sophisticated methods are being developed so that we can pick up the light from extrasolar planets and look at the spectral features and see whether there are biosignature gases in their atmosphere. Here's an example of the spectrum of planet Earth, and you can see that across the infrared there are dips in the light caused by particular gases. We've got dips in light caused by water vapour in the atmosphere, carbon dioxide and even oxygen. These are the sorts of spectra that we'd be looking for in the atmospheres of extrasolar planets. Now, of course, the spectra that we get from extrasolar planets won't be quite this detailed because we haven't got telescopes that can resolve spectra to this level of detail. But it's a good example of the sort of effects of gases on the spectrum of light given off by a planet, and the way in which we can use these dips in the light caused by absorption of particular areas of radiation by gases as a method to look for biosignatures of life on other planets. One of the things that astrobiologists have to decide is which biosignatures should be prioritized, which ones should we look for and give greater priority to when we're looking for life around other stars. Well, for example, we could look for oxygen and ozone. This seems to be the most reliable biosignature of life that we know to date. Certainly the 21% oxygen that we find in our own planetary atmosphere can only be produced by biology, and we would expect that to be the case in other planetary atmospheres as well. Signatures of water vapour in a planetary spectrum are also good to find. It's not strictly a biosignature, but it does tell us that the planet might be habitable. There might be liquid water on its surface. Carbon dioxide, again, isn't a biosignature, but it tells us that that planet has CO2 for photosynthesis. That gas might also be used by other types of life to drive metabolic processes. And methane, for example, is also a sign of life, but it's not conclusive. Methane can be produced by non-biological processes. And so on and so forth. By looking at particular gases, we can develop priorities of the most reliable biosignatures, going from gases like oxygen and ozone through to other gases that may not be biosignatures, but might tell us that a planet is habitable. So what have we learned? We've learned that biosignature gases are detected by using telescopes on land or in space to measure the electromagnetic spectra of planetary atmospheres, particularly in the infrared. We've learned that separating atmospheric spectra from stellar background radiation is a major challenge, particularly for very small and Earth-like planets where the light being given off is very little and much less than the starlight being given off by the parent star. We've learned that transiting planets passing in front of their host stars are useful to life detection because their spectra are relatively easy to study. And we've learned that spectra provide information about both the presence and abundance of different biosignature gases, in addition to the possible water content of the planetary atmosphere and other information about its general atmospheric composition. We've also learnt, though, that interpreting spectral data is highly complicated and requires an understanding of many different factors, not least the technical specifications of the telescopes you're using to detect this light spectra, but also understanding what sort of gases might be produced by biology and whether those gases could also be produced by non-biological processes. But nevertheless, this is a very exciting area of astrobiology, trying to decide what sort of biosignatures we could look for to detect life on exoplanets.